All right, seventh grade. So at this point, we have made a prediction, collected our raw data, organized our data into stem and leaf plots for our male and our female, and then we have found the 5-number summary for our male and female. So now it's time to move on to the next page, where we are going to find our range, interquartile range, mean, and mode. So if you go back to your vocab and remember that range is your maximum number minus your minimum number, so your highest minus lowest. Well, luckily, we have that data right here. So for males, my maximum is 100 and my minimum is 28. So I am going to take 100 minus 28, and that is my range. Okay, so 100 minus 20 is 80. 80 minus 8 is 72. So the range of my data for the males is 72. Now, interquartile range, if you remember, is your upper quartile, which is this right here for me, 93, minus your lower quartile, which for us is 62. So we are simply going to take 93 minus 62, and that will give us our interquartile range. So this is, once you have them, these ones are pretty easy to find. And 93 minus 62 is 31. So our interquartile range, 72 and 31. Now, what does this mean? It means the spread of our data is 72. The difference in the number of contacts from my lowest to my highest is 72. That's a pretty spread out. But from my 25% point to my 75% point is only 31, because most of our data will probably fall within that interquartile range. It's definitely not as spread out. So now I want you to find the range and interquartile range of the female. So go ahead and pause this and find that answer. So hopefully we have found that. So our female range, our maximum is 121 and our minimum is 38. So subtract those and our range is 83. For interquartile range, our upper quartile is 113 and our lower quartile is 87. So when you subtract those, you get 26. So when you look at these numbers, if you look at the range, the female data is definitely more spread out. But when you look at the interquartile range, the male data is more spread out. And what that means is probably that the female data has what we call an outlier, or more of an outlier than the male data. And we're going to get more to that. But an outlier is a piece of data that's far away from the rest of your points. Okay, and if you look at the female data, you can see that. Most of our data is down here, right? But then we have up here this lone 38, which is really far away from the rest. So is that truly a good representation of the female data if I include that 38 in it? I mean, I have to because it's part of my data. But when I look, most of the female data is up here, and this one is really far away. The males have that too. It's just that 28 isn't as far away from 57 as 38 is from 76. So the females are a little more spread out, but when you look at the interquartile range, the female data is more clumped up in that 50% zone between the 25% and 75%. And the males, if you look at this, is more spread out. They don't have that clumping together like the female data does. And that's kind of what this range and interquartile range there is telling us. Okay. Now, we're going to find the mean. We have lots of room here because we're going to need room to do that. Okay, this is where the stem and leaf plot comes in nicely as well. So to find the mean for the males, I have to add up all my data points. I could do it from the raw data as well. That part doesn't matter. And then I need to divide by how many I have. There are 10 data points on the male side. So I have to add all these numbers up and then divide by 10. Me, I kind of like to do it on the stem and leaf plot. It keeps me a little more organized. Okay, so remember that 79.5 is not part. So I kind of like to write over to the side. So for the 20s, all I have is 28. For the 50s, I have 57. That's all I have. Then for the 60s, I'm going to add those together. I'm going to take 62 plus 65 and get 127. So my totals for the 60s are 127. For my 70s is 75, my 80s is just 84. Now my 90s, I have 93 plus 93 plus 93. So if I take 93 times 3, the total for my 90s is 279. And then for my 100s is just 100. And then I add those numbers up. Now you may be saying, Mrs. Lang, that's not much of a shortcut, but when you have a lot more data and it's more, you have more in the 50s and 60s, it is. So then I can just add those numbers. less mistakes on the calculator if I'm plugging less numbers in at a time. I don't have to do it that way. I could go right here and just add those numbers up as well, whatever way works best for you. So if I add those, I have 28 plus 57 plus 127 plus 75 plus 84 plus 279 plus 100, and I get 750. So when I add these, I get 750. Okay, and then you want to divide by 10 because I had 10 respondents, and that equals 75. So the average number of contacts, the mean that a 7th grade male in my study has is 75 contacts. Now let's look at this. Does that kind of make sense with our data? Is 75 somewhere towards the middle of the data? Kind of looks like it. Okay, so now I want you to find the female mean. Hopefully you found your female mean to mean 93. You can go ahead and check your work with mine. That was the sum when I added up all the numbers. I got 1,023, and then I do need to divide by 11 because there are 11 data points with the females, so 93. Do not be surprised if your mean is a decimal. I'm actually surprised both of these came out to be whole numbers. You can certainly have a decimal. It could have been 93.1. If you have one of those nasty decimals, you can go ahead and round it to the nearest 10th or 100th, and you can go ahead and do that with your mean. But these both happen to come out to be whole numbers. So now let's find the male mode. If you remember, the mode is the number that occurs the most. Here's another advantage to our stem and leaf plot. You can see that mode a lot quicker and easier than you can when it's just written as raw data, because you can see the repeats. Right away, your eye is drawn to the fact that there are 3 3s here in the 93. So the male data point, they have 3 93s in their data. That means, do I have any other number that's occurring more than 3 times? And a quick glance tells me no. 93 is the data point that is occurring the most, so 93 is the mode for our males. Okay, now when we look at the female data, again, your eye can be drawn to any triples, doubles, whatever. And if you look, we have 87 as a double and 95 as a double. No other data point has more than 2, so I don't have 3 or 4. So the numbers that occur the most are 87 and 95. They both occur the same number of times at double. So the females actually have 2 modes, 87 and 95. If you remember in vocab, I talked about how you can definitely have more than 1 mode. I've had data that's had 3 modes. You can also have no mode. You could have where absolutely every number is happening once. And so there is no mode. That is definitely a possibility. Okay, so now we have our 3 measures of central tendency. Okay, for the males, we have a median of 79.5, a mean of 75, but a mode of 93. So our mean and our median are very close, 79.5 and 75, saying that the middle of our data is somewhere there in the 70s. Our mode is 93. So looking at that, you know, which one is probably the best indicator of the center of our data? In this case, I'd probably say that median of 79.5 or that average. The mode of 93, that's more towards the top of our data than it really is the center of our data. So in this case, we'd say, hey, you know, the better one for us to use is definitely the median or the mean. Now, that outlier of 28 could be affecting the mean a little bit because that's got to be added in. If you look at our female data, okay, our median is 95. So there's 95. Over here, which looks to be about the center of our data, but our mean is 93. That's pretty, our mean is 87 and 95, pretty close to the middle of the data. In fact, our median and our mode are the same, one of our modes, and then our mean is 93. So again, pretty close to the center of the data. They're pretty close to the same thing. We could say this 38 is affecting our mean because it had to be added in and it's far away from the rest of the data. So our median of 95 is probably the best measure of central tendency to use for the females, but they're all pretty close. Now, when your measures of central tendency are all very close like that, that tells you you have pretty good data. You really don't have much for outliers. That 38 is a little bit of one, but not a huge one. So that's really a good sign when your measures of central tendency are all very close like that. And if they're dead on, then it's great. Okay, so moving on to our next, mean absolute deviation. This is going to be quite drawn out. This takes a lot of time. difficult? No. So I'm going to go ahead and write this up for the males and show you how to do it. So I have completed finding the mean absolute deviation for the male data. And so in the purple box is my mean. So all of these 75s are my mean. That was our mean for the males that we had found on the other side. So what I did is I took each data point from our stem and leaf plot and subtracted it from the mean. So I have 75 minus 28. 28 is my data point. Everything highlighted in pink is the data point. 75 minus 57, so on and so forth. And then once the data points got larger than the mean, I took the data point minus the mean so that I always had a positive answer over here. So this is all those data points in a subtraction problem with the mean. So because there's 10 data points, I have 10 subtraction problems. So here are all my answers to the subtraction problems. And so basically, I found the mean of the answers. So I added them all up and got 176 divided by 10 because there's 10 of them. So our mean absolute deviation is 17.6. So on average, our data points are 17.6 away from the mean, and that is what that's saying. So now I want you to do that with the female data. So you're going to have 11 subtraction problems. Remember that our female mean is 93. So we're going to have 93 minus 38, 93 minus 76, so on and so forth. And then remember, when the mean gets smaller than the data points, you switch, subtract them, and then you find the mean of all your subtraction answers. Do you have your answer for the female data? I came up with 15.8. So again, our mean was 93. So I have the mean outlined in purple on all of these problems, and everything highlighted in pink were our data points that I pulled from that stem and leaf plot. And so here are all of the subtraction problems. Here are all of the subtraction answers. So then again, I added up the answers: 55 plus 17 plus 6 plus 6 plus 3 plus 2 plus 2 plus 14 plus 21 plus 20 plus 28, and you get 174 for your sum, and then divide by 11 because there are 11 data points. So on average, okay, the female data points are 15.8 away from our mean. And so what this is telling us is actually the male data is more spread out than the female data is. This is a less of a spread. And so mean absolute deviation is one of those things you can look at. Okay, so that's how you calculate the mean absolute deviation. Is it difficult? No. A little time consuming? It definitely can be, because you do have to do all of those subtraction problems there. So that's the mean absolute deviation. So next, after we have mean absolute deviation, we are going to create a box and whisker plot. And we will go ahead and start that in our next video.